Hello and welcome to this video where we'll be discussing useful descriptors for concentration. There will be 3 of them by the time we're done. The first one you're well aware of and we'll review. It's the idea of molarity. The second one is a similar idea called molality. And the third one, which you haven't seen as much before, is called a mole fraction. And again, we'll cover these all one by one with examples as we go. So we'll start with molarity, as we already know this one. We know that the units are moles of solute divided by the liters of solution. And generally, we've trained ourselves, and this is perfectly fine, to assume that however many liters of solvent is the same as the liters of solution. And so we see problems like this. So when I look at this problem, I see that it's asking for 3 different ions, right? They're asking for the molarity of magnesium ion, they're asking for the molarity of nitrate ion, and the total molarity of all the ions. So when I'm said and done, I'm setting up 3 different problems, right? I need the molarity of magnesium 2+. I'm going to need the molarity of nitrate ion, right? NO3-. And I'm going to need the total molarity, right? Magnesium and nitrate. And I hope it makes sense in your mind that the total molarity is just going to be adding up whatever I get for the magnesium 2+ and whatever I get for the nitrate. Where am I getting this from? Well, when I look at the problem, I see that my solute must be this 1.05 grams of magnesium nitrate. Right, again, my solute right there. What about my solvent? That appears to be the 75 milliliters of water. And by the way, we know that we're going to need moles of magnesium 2+ divided by liters, which we now know is 0.075 liters in all of these. And so now we just have to be getting to the mole idea for these things. And so when I set that up, it's not too bad, right? We've done this before. I know that there's 1.05 grams of magnesium nitrate. And now let's remind ourselves, magnesium is a 2+, nitrate has to be balancing out that way because there's 2 of them, right? I know that there's 0.075 liters of solution. And now I know that I need the moles of magnesium. Well, the first thing I better do is turn grams into moles. Since magnesium nitrate is my solid, I better use the molar mass. And when I add up 1 magnesium, 2 nitrogens, and 6 oxygens, I find out that that's 148.31 grams in a mole of magnesium nitrate. Now, I look at that and I see that that is an ionic compound. What am I going to get when I break up? Well, it looks like when I break up I get 1 magnesium. So 1 mole of magnesium nitrate makes 1 mole of magnesium 2+, right? So now I look at this, I see that I cross out the grams of magnesium nitrate, I cross out the moles of magnesium nitrate, I'm left with moles of magnesium 2+ per liter, exactly as I'm supposed to be. Numerically, that comes out to 0.094 moles per liter. And by the way, the total down here, I can go ahead and transcribe that, 0.094 molar magnesium 2+, and I'll add that to whatever I get for the nitrate. What do I notice about magnesium nitrate, though? When I break up a magnesium nitrate, I get 1 magnesium and 2 nitrates. So what does that mean? That just means that the molarity of nitrate is twice the molarity of magnesium, right? I have 1 of these and 2 of those. So apparently the molarity of the nitrate is just 2 times the 0.094 that I got up here. So it's equal to 0.19, by the way, when I multiply those out. And so now I can go ahead and add that together, 0.19 molar, and I get 0.28 molar as my total molarity. I have to add together all the ions. Let's try another one. So here we go. Now we've got a problem where we were provided with the molarity of the solution we wanted and the volume. We were provided with the molar mass and the name of the solute. And we were provided with the density of the solvent. I'm going to let you try this. Pause it and see what you can come up with. What I want you to know, though, is that at least one piece of information given here is extraneous. So again, pause this, give it a try, and let's see what that solution comes out to and if it comes out similar to what I get. All right, I hope you came up with about 9 grams, 9.16 grams of benzoic acid. What did we do? We started with the molarity that we were given. We multiplied by the volume of the solution which we were given, and that crosses out the liters. And then all we did was turn moles of solute into grams of solute, and so that's where we get the 9.16 grams. Again, you're familiar with this. Now we're just going to twist it slightly for a new concentration unit. Our new concentration unit is called molality, right? And sounds very similar to molarity, but they're not exactly the same. Our units are different. The way that we define molality is moles of solute, right? Same as molarity there. It's always the moles of solute in the numerator. But down in the denominator this time, it's the kilograms of solvent. And so it's really important with molality problems to keep track of which one's the solute and which one's the solvent so that you can remember how to work them from there. So let's try a simple molality problem with the aqueous solution we worked with before. So remember a couple of slides back, we had a problem where we dissolved 1.05 grams of magnesium nitrate in 75 mils of water, right? So again, we make very sure that we remember that this is a solute and this is a solvent. And then we wanted the molalities of magnesium ion, nitrate ion, and total ions. So again, I can set myself up for moles magnesium 2 plus in kilograms of water, moles of nitrate in kilograms of water, right? The molality of magnesium, the molality of nitrate, and the total molality. And just like before, if I'm talking about all the ions, I can just add up what I get for magnesium and nitrate. So the big key here, right, we know how to do the moles, we did that last time. Now we need to figure out the solvent and the kilograms of the solvent. So let's think about that for a second. If I have 75 milliliters of water, I know that its density is 1 milliliter and 1 gram. And by the way, 1 kilogram has 1,000 grams in it. What do I come up with? I come up with 0.075 kilograms of solvent. I really like molality problems when I have water. Why? Because the molality equals the molarity. Only because this is water. Right? So this is still 0.094 molal. By the way, for molality, we use little m instead of big M, so 0.094 molal. This is still twice the amount of nitrate as magnesium, so this is still 0.19 little m for molal. And this is still a total of 0.28 molal. Again, only when H2O is the solvent. I cannot stress this strictly enough. You watch your problem. If water is the solvent, you can get the same molalities and the same molarities. But that's why we did another molarity problem where we had water not being the solvent. Let's see what happens then. So here's a new problem where I find that my solute, right, benzoic acid is definitely my solute, is not dissolved in water. Look, here's my solvent. What am I adding? 100 milliliters of acetone. So that's my solvent. And you notice that its density is not 1 gram per milliliter. So 100 milliliters of acetone just isn't 100 grams or the 0.1 kilograms. That's important because we need this time, the moles of solute benzoic acid per kilogram of acetone. So we need to get that figured out for ourselves. And what do I see? I also see an extra little helpful descriptor that'll get me further, 0.75 molal solution. So I see that little m, and the alarm bells start going off because little m means moles per kilogram. So I'm going to actually start my problem with that. I'll start with the fact that I need 0.75 moles of benzoic acid per 1 kilogram of acetone. That's the definition of 0.75 molal. And now I need to start thinking about what I have to get to that point where I know the kilograms of acetone. Well, I know I have 100 milliliters, and we know that the density is 0.785 grams per milliliter. So let's go ahead and multiply by the volume like we would in a molarity problem, right? There's 0.1, and actually I'm going to keep it as 100 milliliters for reasons that are going to make sense in a second, right? Because my density, 0.785 grams in a milliliter, right, this is acetone, I'm going to use capital AC for acetone, is going to help me get to the place I need to get, because now I have 0.785, so there's my 1,000 grams in a kilogram, right? So my kilograms are canceled, my milliliters are almost canceled, there they are. Now I'm left with grams and moles, so apparently I need to go ahead and do just a little bit more work. Because when I multiply all of this together, I get an answer of 0.0589. But when I look at my units, what I'm left with is moles of benzoic acid. That's fine, but I wanted to know the mass of benzoic acid at the beginning, so I just need the last step of multiplying by the grams per moles, the molar mass. And that's how I find out that it takes 7.19 grams of benzoic acid. Right? Molality and molarity are not the same when I don't have water. This is not the same number that we got in the last problem, and that's correct because the solvent is not water. Let's look at one more useful version of concentration. So our last two descriptors of concentration, molality and molarity, spent a lot of time paying attention to the moles of solute and the moles of solvent. Mole fraction is one that we use when we don't really care about the amounts of stuff, because the way the mole, or the amounts of stuff in terms of volumes and which one's a solute and which one's a solvent, because the way I define mole fraction is, first off, we use the Greek letter chi, right? And n is just whatever the compound is that we're referring to. So chi n is just equal to the moles of that thing, moles n, per total moles present. It's useful in some cases, especially when we're talking about liquids and liquids or gases and gases, where the numbers are more comparable to each other. So let's just do one quick mole fraction problem. Let's work with that same solution of benzoic acid, and we now know that we make it by dissolving 7.16 grams of benzoic acid in 75 milliliters of acetone. And so if I wanted the mole fraction of benzoic acid, right, I'd just be trying to find chi of benzoic acid. What would I need? I would need the moles of benzoic acid divided by the total moles. Well, we know the moles of benzoic acid. We found that out last slide if you just scroll back a little bit, right? It was 0.0589 moles. And the total moles, right, the 0.0589 are part of that, but I'm going to have to also add the moles of acetone. So I better find the moles of acetone really quickly. And this is where things get slightly trickier, right? Because I have 75 milliliters of acetone. Okay, well that's not too hard, right? I have the density of acetone that I can turn 0.785 grams to 1 milliliter, right? Those will cancel each other out. And now I just need to turn grams into moles, 58.09 grams in 1 mole. Turns out that that's 1.35 moles of acetone. So I have to add that to my total, 1.35 moles. And when I take 0.589 divided by the sum of those two numbers, I find that the mole fraction of benzoic acid is 0.042. So there's a very small amount of benzoic acid present, right? About 4%. That makes sense because that's the solute. By the way, I could easily find the mole fraction of acetone at this point. Why? Because the only two things that are there are benzoic acid and acetone. I could go through this whole process again, where I take the moles of acetone and divide it by the total moles. I could do that calculation again. Or I could just say that the benzoic acid plus the acetone has to equal 1. Why? Because it's 100%. That's all there is. So I could just do 1 minus chi benzoic acid. That's because this has two components in the solution, of course. Right? So I would find out that this is basically a solution that's 96% acetone. Makes sense again. Solvent. So we've got these 3 units of concentration now. We've got molarity, moles per liter. We've got molality, moles per kilogram of solvent. And we've got mole fraction, which, by the way, this is not a mistake. Totally unitless. Why? Because I had moles in the top and they cancel the moles in the bottom. Moles and moles cancel. So I expect mole fraction to be unitless while the other two carry the right units according to what you're talking about.